So in this video, we are going to prove that perpendicular lines have slopes that multiply to make a -1. So, theorem. Two non-vertical lines are perpendicular if and only if the product of their slopes is equal to -1. But how do we prove this? And more precisely, what this means is that this could go one of two ways. We could say that if the two lines are perpendicular, then the product of their slopes is equal to -1. But also we could say that if the product of their slopes is equal to -1, then they're perpendicular, right? Either way. So in order to prove this, we have to consider two cases. The first case we will consider is we will assume that the product of their slopes is equal to -1, and we will prove that the two lines are perpendicular. So let's start out with that into consideration. So we are given two lines, y equals rx plus a, y equals sx plus b. But we are going to assume that the product of their slopes is equal to -1. Therefore, we are assuming that rs is equal to -1. From this information, prove that the two lines stated here are perpendicular. Now, to start out, because rs is equal to -1, we could divide r on both sides. We would get s is equal to -1 over r. And it's perfectly fine to divide r on both sides, because r cannot possibly equal 0. The reason why is because if we have two numbers multiplying to make a non-zero number, then neither of these numbers can be 0. So we're perfectly fine to divide by r here. Therefore, we can replace s with -1 over r. Just like that. So now that we have that in mind, this is essentially what's going on here. We don't really need this anymore. Now we're saying we're given these two lines. Now we want to prove they're perpendicular. Well, to do that, let's first start out by drawing these two lines. For simplicity, let's say that these two lines have distinct y-intercepts. So we're going to say that our first line looks something like this. So this is y equals rx plus a. And our second line looks something like this, right? This is our second line, y equals -1 over r, x plus b. We want to prove that these two lines are perpendicular. Right, well, from this information, we know that their y-intercepts are located here and here. I'll call this point B and I'll call this point A, where the y values of those 2 points are lowercase b and lowercase a. There's a point of intersection right here. I'll call that point C. And we'll say that the coordinates of this point is x0, y0. Because x0, y0 lies on both of these lines, we can substitute these two coordinates into both of these equations. For the first equation, right, in other words, for the first equation, line 1, we can substitute x0, y0 into this. You would get y0 equals rx0 plus a. For equation number 2, same thing, y0 equals -1 over rx0 plus b. Because we have two things equal to the same thing, we can set these two things equal to each other, right? So now from here, I am going to algebraically solve for x0. To do so, I will first start by multiplying r on both sides. If you distribute r on the left side, you get something like that. If you distribute r on the right side, you get something like that. Again, we're solving for x0. I'm going to then add x0 to both sides. That cancels out. I'm then going to subtract ra on both sides as well. That cancels out. So notice, this is what we're going to be left with on the left side. This is what we're going to be left with on the right side. On the left side, I can factor out x0. If we do that, we're going to get left with r squared plus 1 in the parentheses. On the right side, we can factor out r. We'll be left with b minus a in the parentheses. To solve for x naught at this point, all I have to do is divide r squared plus 1 on both sides. And so that goes away, and you're left with x naught is equal to this. And so this right here is equal to x naught. And so I'm actually going to write that for safekeeping up here. So that is what x naught is equal to. So now that we know x naught, we can determine y naught. All we have to do is substitute this into one of these equations. Doesn't matter which one, you're still going to get y naught in the end. But for our purposes, we're actually going to substitute this into both equations. It turns out it's going to be really helpful if we know both ways of expressing y naught. If we were to substitute x naught into the first equation, that is equation number 1, we have y naught equals r times x naught, but x naught is equal to this, so I'm going to replace it with that. And then plus a. From here, we see that r times r is r squared, so we can rewrite it like that. Just like that. So this right here is y naught. But we determined this value by using equation number 1, right? We used equation number 1. But we could also figure out what y naught is if we instead use equation 2. So if we focus on using equation 2 instead, substituting x naught into this equation, you have y naught equals negative 1 over r times x naught, which is this thing, which I'm going to rewrite, just like that, plus b. From here, you can see that the two r's cancel out. And notice how we're doing negative 1 times b minus a. If you recall, whenever we're doing negative 1 times, I'll just write b minus a, this is identical to a minus b if you were to distribute this out. So I'm just going to rewrite that as a minus b. So really, negative 1 times this stuff flips it around to get a minus b. And that's all we have in the numerator. And this is what we get, just like that. So what I'm going to do is I'm going to rewrite these two things right here. So this is where we're at. We have figured out the coordinates of this point. So we know exactly what these 2 points are. So here's the goal. We need to prove that these 2 lines are perpendicular. Well, we can do that if we can prove that this angle is a right angle. And we can prove that this angle is a right angle if we can prove that this triangle is a right triangle. And we can prove that this triangle is a right triangle by proving, right, what we must prove is that AC squared plus BC squared equals AB squared. In other words, we need to prove that this triangle obeys the Pythagorean theorem. It obeys, right, we need to prove that it obeys this relationship between its side lengths. If we can do this, then that means that the triangle is a right triangle. AB is the easy one, right? AB is equal to this length right here, which is just the difference between the y values, b minus a. Therefore, AB squared is just b minus a squared. So now, we're going to evaluate AC and BC squared. These ones are a little different. Let's start with AC squared. It involves using the distance formula, right? Because really, it's the distance between 2 points. If you recall, this is going to be the distance between the x coordinate squared plus the distance between the y coordinates squared. But really, you got to know what the corresponding coordinates are. In the case of the x coordinates for AC, this is technically 0, a, so it's x naught minus 0. For our y coordinates, it's y naught minus a. So really, now we're going to perform the substitutions for x naught and y naught. For x naught, this is x naught, and we're taking this thing and squaring it. So really, it's going to be this thing squared. Just like that. Now for y naught minus a squared, it turns out it's really convenient. We're going to choose the first one, because if you do y naught minus a, that's exactly what you have here without the plus a. Right, and we're taking that thing and squaring it. Just like that. And so when we square this stuff, here's how I'm going to do it. we have r squared b minus a squared r squared plus 1 squared. I'm going to give each of these factors a square. Just like that. And same thing for this one, right? R squared squared in this case is r to the 4th. And so this is what we get for AC squared. As you can see, it looks pretty big, but we will survive. I like that word, survive. So this is what we get. So now we need to evaluate what BC squared is, right? Which involves using the distance formula for these 2 points. Now in this case, our x coordinates is going to be x naught and 0, because again, we're on the y-axis, so it's going to be x naught minus 0. For our y coordinates, y naught minus b. So, just like last time, for x naught, we're taking that thing and squaring it. And for the y naught minus b, instead of choosing this one, we're going to choose this one, because all you're doing is you're taking this and subtracting b. So what you have here is exactly what you have here, just without the plus b. So really, we're taking this thing without the plus b and squaring it. Just like that. And so now we're going to expand out, just like we did before, we're just going to square each of the individual parts. And so this is what we get. Now, something that we can all agree with is that a minus b squared is identical to b minus a squared. And so I'll leave this as an exercise for the audience. I like saying that. I'll leave this as an exercise for the audience to make sure that they understand why this is true. And so you can just flip these around, it's going to be identical. So I know it's a little small, but this is what each of these things are. And all we got to do is prove that if we add these 2 things, it results in this thing. So we're going to prove that now. And so I'm going to use the purple marker for this. So we're adding these 2 things, and we're going to prove that it results in this thing. So I'm going to rewrite this thing right here. Right, so I've rewritten the first one. Now I'm going to add the second one to it. So as you can see, I'm taking this and I'm adding this to it. This is essentially AC squared plus BC squared. We're going to prove that it is identical to AB squared, in other words, identical to this. The first thing that you can realize is that each term here shares the same 2 things. They all share b minus a squared over r squared plus 1 squared. So we can factor that out. And we're going to be left with r squared plus r to the 4th plus r squared plus technically a 1. And we can simplify this to saying r. But what you need to recognize here is that this is identical to the thing we have in the denominator, because this is a perfect square trinomial. If you were to actually expand this out, you would get this. So you can agree with it. These 2 things cancel out and you're left with b minus a squared. And so this proves that if we add these 2 things together, we get this. So what we've essentially proven here is that AC squared plus BC squared equals AB squared. Therefore, this triangle is a right triangle. But not only is it a right triangle, it's a right triangle such that there exists a right angle at angle C, because that's exactly how it worked, right? Showing that this relationship holds means that AB squared is the AB is the hypotenuse of the right triangle, and the angle opposite the hypotenuse is the right angle. Therefore, angle C is the location of the right angle. And because it's a right angle, that is enough to say that these 2 lines are perpendicular, because that is the definition of perpendicular lines. Perpendicular lines form right angles. And that's it. So now we have proven that if 2 lines have slopes that multiply to -1, then the 2 lines are perpendicular. So now we got to prove it the other way around. If 2 lines are perpendicular, then their slopes multiply to -1. So now we are going to say that we are given 2 lines y equals rx plus a, y equals sx plus b, and we're now going to say that we are given that the lines are perpendicular. And from this, we will now prove that the two slopes multiply to make a -1. In our drawing, we can say that this is the first line, y equals rx plus a, and we will say that this line is the second line. Again, we're assuming for simplicity that the y-intercepts are distinct. And so from here, we can label some points. Right, we'll call this point B, call this point A, and we will say that B and A are the values, or the y values at those points. We can call the point of intersection a point C. Now, by the way, since we know that L1 is perpendicular to L2, they're perpendicular, so perpendicular lines form right angles by definition. Therefore, angle ACB is a right angle. So we're able to say that. Angle ACB is a right angle. Well, this means that triangle ACB is a right triangle. And it's a right triangle, meaning it obeys the following relationship between the side lengths. AC squared plus BC squared equals AB squared. So now, we aren't proving that this is true. Because the lines are perpendicular, this is already true. This statement is already true because the lines are perpendicular, right? And we're going to use this to our advantage to prove that RS equals -1, which is pretty cool. But to prove that, we have to determine what this point is. Again, we're going to call that x0, y0. So let's determine x0, y0. Now, again, because x0, y0 lies on both of these lines, that means this point must satisfy the equations of both of those lines. So just like last time, we can write y0 equals rx0 plus a, y0 equals, in this case, sx0 plus b. But because these two things are equal to the same thing, we can set them equal to each other. And from here, we can algebraically solve for x0. I will start by subtracting sx0 on both sides. And you know what? I'll also subtract a on both sides at the same time. So that goes away as well. This is what we're left with on the left side. This is what we're left with on the right side. On the left side, we can factor out x0, so we get r minus s. And on the right side, we have b minus a. From here, we can divide r minus s on both sides. Now, the reason why we can divide r minus s without worrying whether or not r minus s equals 0 is because it's impossible for r minus s to equal 0. If r minus s did equal 0, then the slopes would be equal, which would imply that the lines are parallel, which that's not the case. They're perpendicular. That was good, right? That goes away. We're perfectly fine to do that. So we have b minus a over r minus s as the result for x0. Looks a little bit simpler than it did in the previous case. So now that we know what x0 is, we can evaluate y0. But of course, just like last time, we're going to evaluate y0 from both equations, right? We love doing that. We love evaluating that. Okay, we're doing the same thing we did last time. So we're going to evaluate y0 from equation 1 and evaluate y0 from equation 2. For equation 1, we'll substitute x0 into there. Just like that. And for equation number 2, it's the same thing, just substituting x0 into the other equation. Just like that. And so I'm going to rewrite these two things right here. So now we are going to determine AC, BC, and AB. Because then we can substitute that into there and somehow find a way to prove that RS is equal to -1. Evaluating AB is the easy one. And so when we evaluate AB, we know it's just going to be the difference between the two y values of these 2 points, b minus a. But remember, we want to apply it to the Pythagorean theorem, so we're actually looking for the square, right? Because we're going to need the square of each of these side lengths in order to apply it to the Pythagorean theorem. So that's AB squared. Next, we are going to find AC squared. But to find AC squared is a little bit more complicated because it's going to involve the distance formula. And so from here, we need AC. So it's going to be, remember that's an x coordinate of 0, so it's x naught minus 0 squared. And for the y coordinates, it's going to be y naught minus a squared. Now from here, for the first one, we have x naught squared. So it's just this thing squared. And for the second part, it's y naught minus a squared. And again, there's a reason why we evaluate both versions of y naught. It's because we can conveniently use the first one, because y naught minus a is exactly what we have here without the plus a. So what we got to do is write this as, and so then from here I'm just going to square both of these. Right, and I'm just going to rewrite this right here. So now we have one more side length left to evaluate, and that is BC. So to calculate BC squared, same sort of idea. We're going to be using the distance formula, right? And so now we have to identify x2, x1. Well, x2, x1 is going to be x naught minus 0. And for the y coordinate, it's going to be y naught minus b. And just like for last time, x naught squared is exactly what we had here. And for the y coordinate, we have y naught minus b. Well, it's going to be convenient if we choose the second form of y naught, because if you think of y naught minus b, it's exactly what we have here without the plus b. So we're really just going to take exactly what we have here without the plus b and square it. Just like that. And so again, just like I did for this one, I'm going to square each of the individual parts. And I get that. Again, I'm going to rewrite this up here. And so that is each of the three side lengths squared. So now we can apply the Pythagorean theorem. As I said before, right, before I erased it, right, because this is a right triangle, we know that the Pythagorean theorem holds true. So really, this plus this is in fact equal to this. So I'm going to write AC squared, and then I'm going to add this to BC squared. So we have that, and we can indeed set this equal to this because it obeys the Pythagorean theorem, right? So this is in fact equal to this. But as you can see, it's pretty nice because we can divide b minus a squared on both sides. Again, this is perfectly fine to do, right? B minus a squared cannot possibly equal 0 because for this particular case, we were assuming that the y-intercepts were distinct. So it's perfectly fine to do this. Right, on the right side, it's just 1. But on the left side, that will cancel out with all of these. And so this is what we get. And so at this point, we are going to multiply both sides by r minus s squared. Just like that. On the right side of the equation, we're quite obviously going to get r minus s squared. But on the left side, you can see that when we distribute it across, all of the r minus s's are going to go away, or all the r minus s squareds are going to go away. And so essentially, it'll cancel out with all of these. And so what you're left with is just what we had in the numerators. And so that's really what we have here. So we're left with r squared plus s squared plus 2 equals r minus s squared. I can expand this out. If you FOIL this out, you're going to be left with r squared minus 2rs plus s squared. I can subtract r squared and s squared on both sides, and those would go away. You're left with 2 equals negative 2rs, but then you can divide negative 2 on both sides, you get that negative 1 equals rs. So we've proven it both ways. And it took like 5 minutes. That was good, right? I had to say, it took like 5 minutes to do. 5 minutes, done. I did this in 5, oh, I'll stop, that was bad, okay. But you can see that it holds true. right? Two non-vertical lines are perpendicular if and only if the product of their slopes equals -1, right? It goes either way, whether or not, either way, right? If you're given this, you can prove this. If you're given this, you can prove this, which is really cool. And again, it took us 5 minutes to do it. That was good. It took 5 minutes. And so that's basically it, right? 5 minutes.